Hello, welcome to Special Relativity Part 2. In Part 1, we derived this equation on the left-hand side, comparing the time as measured in the moving frame, let's say the frame of the train or a spaceship, that would be t prime, and the time measured by somebody outside of the moving frame at rest relative to that. And we saw that time in the moving frame between two events was greater, longer time interval passed for the same beginning and ending than for the person standing outside. Now, the two observers don't agree on time. Well, there are also several other things they are not going to agree on. Another one is called the length. So let's say this is a spaceship traveling through space at speed v. Inside the spaceship, the person could maybe pace out the spaceship's length and say it's 100 meters, right? Well, the person outside the spaceship, if they're measuring the length from when the front of the spaceship passes to the end, since they don't agree on times, they're not going to agree on that length either. Say if this person had a stopwatch out here and was measuring, started the stopwatch when the front of the spaceship hit, stopped the stopwatch when the end of the spaceship hit, and based on the velocity, and the velocity equals distance divided by time, calculating the distance or the length of the spaceship, they are going to actually measure a shorter length. It's called length contraction. And again, as with time, the faster the spaceship is going, the bigger v is, then the bigger that length contraction. So something going 99% the speed of light is going to appear very, very short, much shorter than it would be if it was at rest. All right. Another thing that our observers are not going to agree on is going to be the momentum of an object. Another thing they won't agree on would be the velocity of an object. So let's take a look specifically at the relativistic momentum, because we are going to use that to derive unarguably probably the most famous equation in the world. You tell people F equals ma, yeah, if they took physics, they're going to know what that is, Newton's second law. But you say E equals mc squared, they're going to know what you're talking about. And so here is the equation for the relativistic momentum of an object of mass m moving at speed v. And we can see that as v gets larger and larger and larger, then our denominator gets smaller and smaller and smaller, so the relativistic momentum increases. Take that to the extreme and say that you've got an object traveling at the speed of light, so v is equal to c. Then you get 1 minus 1 on the bottom, you get 0 in the denominator, and essentially your momentum is infinite. This is why the speed of light is considered the speed limit in the universe, because nothing with mass can attain the speed of light. Some people think of it this way, is that as an object's speed increases, then its relativistic mass increases, and it would become infinite at the speed of light. So anything with mass, even a tiny subatomic particle like a proton, in order to get it to the speed of light, since it would have an infinite amount of mass at that point, you would essentially have to expend an infinite amount of energy to accelerate it from 0.999999 times the speed of light to the actual speed of light. So since we cannot expend an infinite amount of energy, this is the speed limit for the universe. Now we are going to use this to develop the most famous equation in history, E equals mc squared, and we're going to start at a very familiar place. We're going to start at F is equal to dp dt. This is, of course, Newton's second law. The net force is equal to the change in momentum over the change in time. All right, now we're going to do something a little tricky. All we're going to do is multiply both sides by dx. All right, and the immediate reason I want to do that is because I know that the integral of force with respect to position is the work done, and I know that the work done, the net work done, is equal to the change in kinetic energy of an object. That's going to be the energy term that we're looking for in E equals mc squared. And on the other side, I multiplied by dx as well, and we're going to move our dt over to be underneath the dx. So dx dt should be very familiar to us. That is the velocity of an object. So rearranging here, or just rewriting, f dx is equal to v dp. Now we've got a differential equation here. We're going to integrate both sides. So integrating f dx and integrating the velocity with respect to momentum. Now on the left-hand side, we get the work done, integral of force with respect to position, which we're going to rewrite as the change in kinetic energy. On the right-hand side, now this is where it gets a little tricky. We can't integrate velocity with respect to momentum because we have momentum as our variable of integration. So we are going to use our equation up here for the first step, because this object, we do have to consider its relativistic momentum. So we need to take the derivative of that thing up there with respect to velocity. That's going to allow us to change the dp into something in terms of a dv, and then we can integrate. Then we can integrate it. So step one, we're going to use the quotient rule to take the derivative of this with respect to v, and then we are going to integrate. All right. So step one. Okay, so we're going to take the derivative of the relativistic momentum. So that means we're going to take the derivative of mv over the square root of 1 minus v squared over c squared. I replaced the square root with raising it to the 1/2 power. And we're going to use the quotient rule, which I remember from my high school calculus as bottom times the derivative of the top. So actually, before I even start this, what I would recommend is that you pause the video here, go ahead and take your derivative, and let's see how you do. Okay, so remember the quotient rule, and anytime you take the derivative of the velocity, remember your chain rule, you're going to have a dv after that. All right, so go ahead and pause it right now and do the derivative yourself. Okay, so here is my derivative of the relativistic momentum using the product rule and, the quotient rule and the chain rule. So I always remembered it as bottom times the derivative of the top. So here is what we had on the bottom, 1 minus v squared over c squared times the derivative of the top, m, and the derivative of v is dv. Now we have minus, okay, so over here, this is going to be the top times the derivative of the bottom. So the top was mv, and the derivative of the bottom stuff. We take the derivative of the outside function, so we get 1/2. Quantity, 1 minus v squared over c squared, and we have to decrease that exponent by 1, so we get a negative 1/2 for our exponent. And we have to use the chain rule, so we'll take the derivative of the stuff inside. The derivative of 1 is 0, and the derivative of negative v squared over c squared is negative 2v over c squared times the derivative of the velocity, dv. And we divide everything by the bottom squared, so squaring the square root, and we get 1 minus v squared over c squared. So now some simplification can happen here. We've got a 2, and that's going to cancel with the 1/2 here. We have a v on the left, and we have a v on the right, so that's going to combine into a v squared. And this negative here is going to make this negative into a positive. And we notice that we also have an m and a dv in both of the terms on the top. So we're going to factor that out. So now I'm going to write the simplified version of this. Okay, so here's my simplified version, even though it doesn't look very simple. I factored the mdv out, and on the top we have the 1 minus v squared over c squared to the 1/2 power, plus v squared over c squared out front, times 1 minus v squared over c squared to the negative 1/2, and on the bottom we still have our 1 minus v squared over c squared. Now I'm going to do something that at the outset doesn't look like it's going to simplify this, but it actually does. I'm going to multiply the top and the bottom by 1 minus v squared over c squared to the 1/2 power. So top and bottom. And we get a dramatic simplification when we do that. So first, distributing it to this guy over here, the 1/2 adds to the 1/2, so we get rid of the square root there. And distributing to this term right here in the top, the 1/2 square root on the top is going to cancel with the square root on the bottom. So we actually get rid of this term. So that term goes away. This one, the square root, goes away. And on the bottom, we essentially have 1 minus v squared over c squared to the power of 2 over 2. And we're going to add the 1/2 here. So we end up on the bottom getting 3/2 power. So let me rewrite this and you can see what I mean by a vast simplification. So cleaning up the mess a little bit, we end up with 1 minus v squared over c squared plus v squared over c squared divided by that same thing to the 3/2 power. So our v squareds minus c squareds on the top cancel out, and we end up with something pretty lovely. That something that's pretty lovely is simply m dv on the top divided by 1 minus v squared over c squared to the 3/2 power. I bet you didn't see that coming. So as a reminder, that was the derivative of our relativistic momentum. All right, so going back to what we had before, we had the work was equal to the integral of v times dp. So replacing the dp with our new equation, we've got mv divided by 1 minus v squared over c squared to the 3/2 power, and that is all times dv. So that is now something that we can integrate, and we're going to use some limits of integration here. We're going to go from 0 to v. All right, so this is a mildly challenging integral. I will say you're going to have to use a u substitution here to get this done, and so I would invite you again to pause the video and go ahead and do your u substitution and see what you come up with for the integral. Make sure you plug in the limits, the v and the 0. Both of them are significant here. All right, so pause it, take your integral, and we'll see how you did. So my substitution here, I'm going to make u equal to 1 minus v squared over c squared. The advantage to that is I just have a u to the 3/2 then on the bottom. Taking the derivative of that, du is equal to negative 2v over c squared dv. And the advantage of that is I end up with a v dv. So in one fell swoop, I am going to change my bottom into just u to the 3/2, and I'm going to replace the v dv with something times du. So if that wasn't immediately obvious to you, go ahead now, again, pause the video, make your u substitution, and do the integral with that as your u sub. So I'm going to continue here. I'm going to solve for v dv, so multiply both sides by negative c squared over 2 du on the left, and on the right we end up with a v dv. So again, I'm going to substitute in that for the u is going to go in there, and the v dv is going to get replaced by everything there. Okay, so making my substitutions here, I again replaced the 1 minus v squared over c squared with u, so I get u to the negative 3/2. That's going to enable me to just use the power rule for integration, writing it that way. And then I replaced my dv with negative c squared over 2, which can come out of the integral, along with the m, and then my du is over here. And we already see an mc squared term. We should get some goosebumps here, right? That's looking promising. So now we're going to integrate this guy, and I prefer to not change my limits of integration. I'm just going to integrate and then resubstitute back in the 1 minus v squared over c squared. So we end up with u to the negative 1/2 power, and then we multiply by that to get rid of the basically the negative 1/2 that we get if we take the derivative again. And then out in front here we have negative mc squared over 2. All right, so simplifying, what do we got? Let's see, this negative cancels this negative, this 2 cancels that 2, and we end up with mc squared, again, some goosebumps. Putting our v back in, we got 1 minus v squared over c squared, and let's go ahead and just put the square, that's going to be 1 over the square root, and then we are going to evaluate that from 0 to v. Okay, so plugging in our limits of integration. First, we plugged in the v, and we end up with this term, 1 over the square root of 1 minus v squared over c squared, minus, when we plug in 0 for v, we end up with a 0. 1 over the square root of 1, we end up with 1. All right, so that's the plugging in the 0 as that limit of integration. Okay, and let's remind ourselves that this was equal to the change in the kinetic energy, which is k final minus k initial. Since we started at rest, remember our initial velocity was 0, then it's really just k final. So rearranging things, we get k is equal to mc squared divided by 1 square root of 1 minus the now very familiar v squared over c squared minus mc squared. So now a little bit of hand waving here. This mc squared term, that is an energy. It has a unit of joules, so it's divided by our familiar square root of 1 minus v squared over c squared, which is what our relativistic momentum was divided by, which is what our relativistic time was divided by. So we are going to make a leap right here, a little bit of hand waving, and we're going to call this the relativistic energy. So the total relativistic energy of an object. All right, and so we are then going to add this mc squared over to the other side, and we're going to get E, relativity, or relativistic energy, is equal to mc squared plus the kinetic energy, right? So something moving at speed v is going to have a total amount of relativistic energy equal to mc squared plus 1/2 mv squared, right? But if something is at rest, then it doesn't have any kinetic energy. So something at rest would simply have a total amount of energy equal to its mass times the speed of light squared. Wow. So this right here is why atomic bombs go boom. This right here is why stars like our sun are able to convert mass into energy and last for such a long time, because a very tiny amount of mass produces a very large amount of energy, because that's 3 times 10 to the 8th squared. That's a really big number, right? So, if you want to donate your body to science, we can convert all of your mass into energy directly and, provide power for your city for the next decade. Unfortunately, most of the atoms that make up your body are incredibly stable and are very difficult to either split or fuse into other atoms. So therefore, it's not quite so simple, right? But this is earth-shattering, and let me remind you that this was published in 1905, right? This didn't get experimental confirmation until the 50s. 40s, we'll say, when they actually exploded the first bomb. No pun intended, earth-shattering consequences here, earth-shattering consequences. We use this to power nuclear power plants to give us, essentially carbon-free energy. We use this to build incredibly devastating bombs. And potentially in the future, we could use nuclear fusion to give us limitless clean energy, where hydrogen is the fuel and the byproduct is helium, an inert gas, no pollutant. Take a step back here, right? We basically used those 2 first postulates from Einstein, that the laws of physics are the same for any inertial reference frame, and that the speed of light is a constant for any observer in any inertial reference frame. And we used Pythagorean theorem and a little bit of algebra to figure out that time is relative based on how fast you're going. And we used first semester calculus to come up with the most famous equation of all time. That's pretty phenomenal, okay? And again, this is not science fiction. This gets confirmed every second of every day in a nuclear power plant producing power, all right? It's pretty amazing. And as amazing as this is, and as unrealistic as you might think it is, wait until we talk about general relativity, where Einstein figured out how to apply these relativistic ideas to the more general case, any frame of reference, accelerated or not. And remember that Newton got around the whole accelerated frame of reference thing because we are in an accelerated frame of reference. Go jump out the window, you'll find out. Newton invented gravity. That's the reason things accelerate with no apparent force acting on them. Einstein disagreed. Unfortunately, though, the math is not quite as simple as special relativity. Einstein himself needed help with it, and it took him 11 years to come up with general relativity. And general relativity, as difficult as it was actually confirmed far before special relativity. And it turned Einstein into the first scientific rock star. So that is it for today. Thanks for stopping by.